let's begin today with a blast to the past, a problem we learned how to do in elementary school. Say 2,934 divided by 5, keeping in mind that a fraction is really just division. So we might have heard the question, divide, or we might have gotten the question, convert to a mixed number. Both of these amounted to performing a process we called long division. So we said 5 does not go into 2, but 5 does go into 29, 5 times. We said 5 times 5 is 25. Then we subtracted that, 4 is left over. We bring down the next place, 5 goes into 43, 8 times. 8 times 5 is 40, take it away, left over is 3. Bring down the 4, 5 goes into 34, 6 times. 6 times 5 is 30, subtract, and you get a remainder of 4. And we wrote this as 586 and 4/5, also known as 586 plus 4/5. So vocab here is going to be pretty key. The thing up here, this is what we call the dividend. The bottom is what we call the divisor. Those are nice to know, but the most important ones right here are quotient. This is how many times 5 went into that. And this number right here is the remainder. Okay. What we want to do today is this type of problem, except with a polynomial divided by another polynomial. Now, we're going to do something just like this with an algorithm that we will call polynomial long division. It goes like this. I'm going to take the dividend, write it down. Then I'm going to write the divisor on the outside. Then, like we did here, I'm going to say how many times does this go into that? But the phrase go into here means something very specific. We're going to define it as how many times does x go into x cubed, first of all, and we're looking for something that has the form of a polynomial. So x multiplied by x squared will get x cubed. So I'm going to write x squared here in the space where the quotient will go. X squared times x plus 4. I'm going to write x cubed plus 4x squared. Then I'm going to subtract all of this. Those will cancel, and 3x squared minus 4x squared gets me negative x squared. So if you establish the parallel, right? So 5 goes into 29 5 times. There's where the quotient goes. Then I said 5 times 5 is 25. Take it away and see what happens. Over here I said, how many times does this go into that? It goes in x squared times. That's the beginning of my quotient. That, x squared times x plus 4, goes right here. Then I'm going to take it away to see what I have left. The next step is to bring down the next place, or the next term in this case, and say how many times does x go into negative x squared, just looking at the leading term. It goes in negative x times, because negative x times x is negative x squared. So we'll say, here, we'll take that part of the quotient, negative x, and multiply it by x plus 4. That gets me that. Negative x times this is that. And then I'll subtract everything. Those cancel. Negative 5x minus negative gets me negative x. Bring down the plus 1. The last thing, x goes into negative x, negative 1 times. So negative 1 times x plus 4 is negative x minus 4. And I'll subtract all of that. These cancel. 1 minus negative 4 gets me 5. So I'll say that right there is my remainder, and I'll put down remainder 5. Okay. To establish the parallel with how we represent our answer, we'll write over here the quotient, x squared minus x minus 1. Then we'll do plus, the remainder is going to go in the numerator, and the divisor, x plus 4, is going to go in the denominator. Just like we have here, we're going to call this the quotient, and this up here is the remainder. Now, before we back away and act very satisfied, we have to remember, when you divide polynomials, you have to qualify that you're not actually dividing by 0. So there is a domain restriction here that says x cannot equal -4. This is something that we don't always have to write, because here it's very obvious that you can't divide by 0. But there are going to be times when maybe there is no remainder, and we don't have this term written, and we have to be very cognizant of the fact that we still cannot divide by 0. Let's do another example with a what if involved. So we want to divide 2x to the 4th minus 20x squared plus 5 by x minus 3. So I'm going to set up my long division, put the 2x to the 4th down, and then I realize there's no x cubed term. So I can leave a blank, or a lot of people prefer to write 0x cubed to remind themselves that there's no x cubed term. If you forget to do that, we're going to have a bit of a bad time. There's no x term, so I'll put down a 0x, and then a plus 5 at the end. And this shall be divided by x minus 3. First step, how many times does x go into the leading order 2x to the 4th? Well, x times x cubed gives me x 4th, and I need 2, so I'm going to put down 2x cubed, and say 2x cubed times x is 2x to the 4th, 2x cubed times -3 is -6x cubed. Then I'll subtract very carefully. Those cancel. 0 minus -6x cubed is positive 6x cubed. Bring down the next term. X goes into this 6x squared times, so I'll put 6x squared in the quotient. That times x is 6x cubed to cancel this. That times -3 is -18x squared. And I'll subtract everything carefully. These cancel. -20 minus -18 gives me -2 with an x squared. Bring down the next term, which is nothing. X goes into -2x squared, -2x times, so I'll put -2x, -2x times x, -2x squared, -2x times -3, positive 6x. Then I'll subtract everything carefully. These cancel. 0 minus -6x. Sorry, I said 0 minus negative. I meant 0 minus a positive 6x. Bring down the plus 5. X goes into -6x, -6 times, -6 times x, and then -6 times -3. And we'll subtract everything very carefully, getting -13 at the end. So we'll say remainder is -13, and I'll write this as quotient and remainder. So my quotient is 2x cubed plus 6x squared minus 2x minus 6, and then for the remainder I can do plus a -13, or I can immediately just put -13 like this and understand that this is the remainder. So to label, this part is the quotient, then this, including a negative, is the remainder. And because I still have a denominator, it's still clear that x is not allowed to be 3, because then I would divide by 0. But it is worth being cognizant of this, and I'm going to go ahead and write that x cannot equal 3 in parentheses. Not necessary to state, but good to know. Another example. Let's put down 3x cubed plus 8x squared minus 5x minus 10. And this time we'll divide by something that isn't just an x plus or an x minus. Let's involve an x squared. The setup is going to be the same structure. We'll have the 3x cubed plus 8x squared minus 5x minus 10, and then we'll put the entire divisor on the outside. We're still looking for how many times does this go into that, leading term into leading term. And it's going to be x squared times x gives me x cubed, and I need 3 more. So I'm going to put 3x for the quotient lined up above the x term. So let's go. 3x times x squared is 3x cubed. 3x times 4x is 12x squared. 3x times negative 2 is negative 6x. I just have more terms, but same algorithm. Then we'll subtract very carefully. They cancel. We get negative 4x squared here, and subtracting a negative means I'll add, so I get that. Bring down the next term. X squared goes into that. Negative 4 times x squared is negative 4x squared to cancel the leading term. Negative 4 times 4x gets me negative 16x. Then negative 4 times negative 2 gets me positive 8. Subtract everything very carefully. These cancel. Subtracting a negative means I'm going to add. Then subtracting 8 means I'll go deeper into the negatives. And then I stop here because x squared, we're saying, cannot go into 17x. I can't take a bigger power and put it into a smaller power. That's part of the rule set that we're using for this process. So we stop and say our remainder is 17x minus 18. When we write this in quotient and remainder form, the quotient will be 3x minus 4, then plus the remainder will show up here in the numerator as always, divided by the entire divisor, like so. So this is the quotient. This is the remainder. Now, you might ask at this stage, what is x not allowed to be in order for us to end up dividing by 0 here? So we could set the denominator equal to 0 and find what would make the bottom equal to 0. Let's try it. So if we say 0 equals x squared plus 4x minus 2, then by the quadratic formula we could say x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. This in here, that's going to be positive 8, so we'll get a square root of 24. And square root of 24 is going to come out to be 2 square root of 6. So we simplify this down and we get x is equal to negative 2 plus or minus root 6. Now, in this case, we got the values of x that make the denominator equal to 0, which is specifically what we were trying to prevent, right? Because we don't want to divide by 0. So our final domain exclusions will be x cannot equal negative 2 plus or minus the square root of 6. Once again, because the denominator still shows up here, we don't need to state this, but it's good to be cognizant. Let's do another example with some new behavior. Here comes x cubed plus 8 divided by x plus 2. So setting it up, we notice there's no x squared term, so we'll leave a 0x squared. There's no x term, so we'll leave a 0x, and we'll put a plus 8 at the back. This we're dividing by x plus 2. So x goes into x cubed, x squared times. X squared times x is x cubed. X squared times 2 is 2x squared. And we subtract everything carefully. They cancel. 0 minus 2 gets me negative 2 with an x squared. Then x goes into negative 2x squared, a total of negative 2x times. Negative 2x times x is negative 2x squared to cancel. Negative 2x times 2 is negative 4x. I didn't bother bringing anything down because it was just a 0. Then we subtract. That minus that cancels. And then 0 minus negative 4x gets me positive 4x. Then bring down the 8. X goes into 4x 4 times. 4 times x is 4x. And 4 times 2 is 8. Ooh, everything cancels. So we have no remainder. We can write remainder equals 0 here. But then when we write this in quotient and remainder form, we would write down the quotient. And then there's no remainder. So we wouldn't bother writing it. Now this is the stage where we say, over on the right, there's no denominator anymore because there's no remainder, so we don't write a term with a denominator. So if we just look from there to the right, we would say that's a polynomial. I can put any value for x into that polynomial, and it would be defined. It looks like my domain is all real numbers. But wait, over here, x plus 2 was on the denominator, which means I cannot put x equals negative 2 into this expression. That would lead to dividing by 0. So I actually have to state x cannot equal negative 2. This is no longer optional. Because there's no denominator to give me that information, I have to state it explicitly. Okay, let's wrap it up. There's an example. I'm just going to use it to reference the pieces. You don't have to worry about going through it for now. Today's lesson, we called this process polynomial long division. It's also called the division algorithm. You might see it referred to as that. So we started with a polynomial function f of x. In this case, this top thing right here is what we're referring to as f of x. And we took that divided by another polynomial function we called the divisor. So this right here, d of x. Okay? This is the divisor. Then we performed this process and we got a quotient which went up here. We're going to refer to this as q of x. It is, once again, a polynomial. So back here, this is q of x, referring to this structure right there. And then we also got a remainder, which we labeled up here, a remainder, which is also a polynomial. And then we wrote that over d of x, once again, the divisor. So going back to here, this went up there and became r of x, and this down here was the same d of x that showed up there. And this form is not only pretty, but the way we've done this is it's guaranteed that we can take a polynomial divided by another polynomial and end up in a form like that where all of these are polynomials. All right, thanks for tuning in. We'll continue to synthetic division next time.